All right. So greetings, YouTube. Beautiful mind here. So we're going to be kind of continuing our discussion. We're moving into chapter 3 for our calculus course. And so let's take a look at it. So chapter 3 is going to be around applications of differentiation. Okay. So we're going to take those concepts that we had before where we were finding the derivative. Keep in mind that the derivative is going to be the slope of the tangent line at a point, right? And so we're going to be looking at some of the applications of differentiation. So we're going to start with section 3.1, using first derivatives to find maximum and minimum values and sketch graphs, right? So the objectives here are to find relative extrema of a continuous function using the first derivative test, and we want to sketch graphs of continuous functions. So let's see. So we have some definitions we want to introduce. We say a function is increasing over an interval I if every a and b in I, so for every a and b in I, if a is less than b, then f of a is less than f of b. In a graphical sense, like as we trace the graph left to right, the graph goes up, right? So whenever a is less than b, f of a is also less than f of b, right? So that's what we mean by a function is increasing. In a graphical sense, again, as we trace the graph left to right, it increases, it goes up, right? We say a function is decreasing over an interval I if for every a and b in the interval I, whenever a is less than b, then f of a is greater than f of b, right? So in a graphical sense, what this means is as we trace the graph left to right, the function is going to go down. Okay. All right. Okay, this is fine. So then we have this theorem. Let f be differentiable over an open interval I. If f prime of x is positive for all x in that open interval I, then f is increasing, right? So if the derivative is positive, then we say that the function is increasing over that I. If the derivative is negative for all x in the interval I, then f is decreasing over the interval I. So remember the slope, we said that the derivative was a slope of the tangent line, right? So if we can consider the slope of the tangent line for all points on some open interval, if all of those slopes are negative, then we say that the function is decreasing. Okay, let's see. So we have some more definitions. A critical value of a function f is any number c in the domain of f for which the tangent line at that point is horizontal, for which a derivative does not exist, right? So we're gonna identify a critical value where basically the derivative where f prime is equal to 0 or f prime does not exist, right? So given a function, our critical values are going to be where the derivative is 0 or whether the derivative does not exist, okay? That's what we're going to mean by a critical value. If c is a critical value of a function, then c comma f of c is going to be a critical point, right? Basically, it's the ordered pair associated with that critical value, okay? Some more definitions. So we say f of c is a relative minimum if there exists within I an open interval I1 containing c such that f of c is less than or equal to f of x for all x in that open interval I, right? So we consider an open interval. We say that a y value is a relative minimum if basically is less than all the nearby y values, right? So then we're going to call that a relative minimum. And then conversely, f of c is going to be a relative max if there exists an I in an open interval, within an open interval I2 containing c such that basically that y value is larger than all nearby y values, right? Okay. So basically, a relative minimum is like the bottom of a valley, and a relative max is like the peak of a mountain, right? So that's the concept. We're going to see it in action. If a function has a relative extreme value f of c on an open interval, then c is a critical value. So then it should be the case that either the derivative should be equal 0 or the derivative does not exist, okay? That's kind of a reiteration, maybe kind of reverse what I mean. For any continuous function f that has exactly one critical value in open interval, let me see. This is the first derivative test for relative extrema. F has a relative minimum at c if f prime is negative on the interval. And f prime, let me see. Minimum. Oh, okay. A to C. Okay. So we have an open interval A, B, and C is somewhere between A and B. C is somewhere in that interval. We say we have a minimum value, right? So if we have a minimum, that should be the bottom of a valley, right? So let me just do a quick sketch. So say we have, if we're considering a minimum, right? We have something like this. To the left, notice that the function is decreasing on the left side of this, and this is our C, and then it's increasing on the right, right? That's what this is saying. So if the derivative is negative on the left side of C and it's positive on the right side of C, then that means on the left is decreasing, on the right is increasing. So that means we're talking about a local minimum, right? And then a relative max is where it's going to be increasing. The function is going to be increasing on the left and then decreasing on the right. So then that means we would have the peak of a mountain, and we're considering a relative maximum. And then we say f neither has a relative max or min if the derivative has the same sign on the left and the right side of that c value, right? Okay. So that's the first derivative test. It's basically we're exploring whether the function is increasing, decreasing, or if it's like a relative extrema, or none of these. Okay. So this is kind of like a pictorial representation, right? So over here on the left, we have a relative min. On the left side of our c value, the function is decreasing. On the right side of our c value, the function is increasing. So if it goes from decreasing to increasing, that means we're talking about a relative minimum. All right. So the sign on the left was negative, the sign on the right was positive. So it's decreasing on the left, increasing on the right. That means we have a relative min. Conversely, say the function is increasing on the left and decreasing on the right, then we're going to be talking about a relative max. Increasing on the left, decreasing on the right. Okay, relative max. Okay. So then here, notice like we still have our c value. Say it's decreasing on the left and it's decreasing on the right. So then there's no relative max or min. It's decreasing on the left, decreasing on the right. Okay, and it's going to be decreasing over that whole open interval. Conversely, say it's increasing on the left and increasing on the right. There's no relative max or min. Okay. So in this example, we're asked to graph this function given and find the relative extrema. Suppose that we're trying to graph the function, but we don't know any calculus. What can we do? We can plot a few points to determine in which the direction of the graph seems to be turning. Let's pick some x values and see what happens. So before I dive into the way they're doing it, I just want to kind of give my own personal backstory. So let me get a copy of this. Let me get rid of this. I want to take this guy. Gonna drop it right here. Okay. And I feel like I'm gonna need some more space. I'm gonna just go ahead and get myself another page. I'm gonna do some paper like this. Okay. So for right now, where we are, we're asked to graph this, right? So some things that we can see off the rip. We have this constant term is 12, so that should be our y-intercept. All right. Notice the highest exponent. So I'm trying to pull as many things as I can from college algebra before we kind of start applying, doing the applications of derivatives. So the y-intercept should be 12. Notice the highest x. This is a polynomial, right? This is a finite sum of monomials, right? So that has some implications. The highest degree is 3. So we might anticipate maybe like an S-shaped curve, right? The leading coefficient is positive. So that means our graph should go up to the right. And because the degree of the polynomial is odd, that means the left side does the opposite. So it should go down to the left. Okay. Let me try to list out. Let me see. So usually when I'm graphing stuff like this, my order. So like one of the first things I do, I like to find, okay, are there any intercepts? right? And it's going to be a little bit jarring initially, but once we've done it like enough times, it'll kind of sink in. So first I like to find any intercepts. I also like to do a test for symmetry. Trying to think of what else. Let's do extrema. So that's like right now we're just going to be doing the first derivative. Okay. And then I'm just going to say a few additional points. So a few additional points. And if I think of other things, I can update this. And then we'll graph. Okay. Okay, so I mean that's just kind of like a rough sketch of like some of the thought processes. Let's actually start with the derivative. Okay, so for f of x, 2x cubed minus 3x squared minus 12x plus 12. Okay, let's first identify our extrema, right? So to do that, again, we said that the critical values are going to occur when the derivative is either 0 or undefined, right? So if we consider f prime of x, that's going to be what? 6x squared minus 6x minus 12, right? That's the derivative. So then if we set that to 0 and solve, so that's going to be like a parabola. So it's never going to be undefined. So we're not going to be able to do that second condition. But then again, if we set it to 0 and solve, 6x squared minus 6x minus 12 equal to 0, we can divide both sides by 6. This will give us x squared minus x minus 2 equals 0. Can we factor it like this? X and x plus and minus 2 and a positive 1. Let's see if this works. 1 times negative 2 that's negative 2, and then 1 plus negative 2 is negative 1, okay? So then from here, we get that what? X equals negative 1 and x equals 2, right? So those are critical values. So we're anticipating a relative extrema when x is negative 1 and x is 2, right? So let me see. So we can plot these critical values on a number line and I do a test, right? So if these are our critical values, these are candidates, we need to do the first derivative test. So we need to look on the left side of negative 1 and the right side of negative 1. We need to look on the left side of 2 and the right side of 2. If the function, let's look at the sign of the derivative on either side of these, right? So first I'm going to plot these critical values. So undo that. Okay, so positive. So the positive x is going to go off to the right. Okay. So then let's see. I'm just going to put negative 1 here. I'm going to put 2 here, right? So then here, f prime of x is 0. Here also f prime of x equals 0, right? At these values. Here's our 0, here's our 0, right? So then let's choose a number to the left of negative 1. Let's say when x is negative 2. So let's look at f prime of negative 2, right? So if we plug in negative 2, this is what? This is going to be negative. This is going to be negative. Double negative is positive. So f prime of negative 2 is going to be greater than 0, right? So over here, it's positive, which means the function should be increasing, okay? Let's choose a number between negative 1 and 2. We're going to choose 0, all right? So we're going to consider f prime of 0. So if we plug 0 in, this is positive, this is negative, the original function is negative, which means that the function should be decreasing. Okay, so then this should be, when x is negative 1, that's going to be our relative max. It should be the top of the mountain, right? And then let's choose a number to the right of 2. Let's say when x is 3. Let's look at f prime of 3. Right? If we plug in 3, positive, positive, so then the derivative is positive, which means the original function should be increasing. Okay? So now we have candidates for our relative max. This is going to be a maximum. This is going to be a minimum. Okay? So we have the peaks and the valleys. We have the y-intercept. Maybe we can find the x-intercept, right? Because again, the y-intercept should be here. If we set x to 0, this is gone, this is gone, this is gone. Only thing that's left is 12. So we got our y-intercept. Maybe we could find, let's see if we can find our x-intercepts. So we have that the y-intercept, we said that's going to be 12. Okay. So for the x-intercept, remember, we need to set y equal to 0. Okay, and solve. Let me just copy this. Okay. Okay, so let's see, can we factor this guy? So then we have this 2x cubed minus 3x squared minus 12x plus 12. We're going to set it equal to 0. So since we have 4 more terms, I'm going to try factor by grouping. Like I'm going to try factor by grouping. So if I look at the first two, what do the first two have in common? They both have x squared, right? And that's going to leave us with 2x minus 3. So the hint is, hopefully we can find another 2x minus 3 on the right hand side. Okay. Doesn't look like it, right? Make sure I got the original right. Because you can factor out a 12, that's just going to be x plus 1. I'm going to try one other thing, and then I might scrap this part, the x-intercepts. Because there's a lot of stuff we could talk about from college algebra. We could do like Descartes rule of signs, the plus and minus zeros, that whole thing, the rational zero test. I'm going to try switching the 2 in the middle and see if that does anything. Let me try that really quickly. So then f of x, we get this 2x cubed minus 12x minus 3x squared plus 12. I switched the 2 in the middle. And I just wanted, I'm going to try factor by grouping again. And there's another one that we can try as well. I mean, there's always several that we can try. So I switched the 2 in the middle. I'm going to see, okay, if I do this arrangement, can I get anything better? So from the first two, we can factor out, looks like what is that, 2x? What does that leave us with? X squared minus 6, that doesn't look promising. Let's see, we can factor out a 3, a negative 3. Okay, let's keep going. If we factor out negative 3, it leaves us with x squared minus 4. Oh, so that's not a square, but so close. X squared minus 4. Okay. So I'm going to scrap that part. I'm finding the x-intercepts there. But we have a good amount of information though. Let me think about it. Because we have the candidates for the relative max and min. We have our y-intercept. That's enough for now. So we could do like a few additional points. Now we don't have the exact x values. I'm trying to think of what else could we do. I mean, there are other tests. You got the rational zero test, the p over q business. For the sake of time, I'm just not going to do that. I'm just gonna at least digest the stuff that we found. Okay, so let me kind of do like this. So what we have a relative max when x is what, -1. So we have a relative max when x is -1. What's the original? That's going to be what? -2, -5. 12 minus 5 is 7, so 19. So it looks like when x is -1, y is 19. I think we also had a relative min when x was 2. So if x is 2, let's see. 8 times 2 is 16, minus what? 12 is 2. Minus 24 is -22. -10, it seems like. Hopefully my math is okay. So we have a relative max, relative min. We have a y-intercept. We said it was what, 0, 12. Okay. So I kind of want to do just a quick rough sketch of what we have. Let me add a page. And it's not, I'm not doing super details here. Okay. Positive x is in this direction, positive y. So at least if we do those things that we found, x's, y's go to 20. So let's see. What if we went 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. X's, we can go 1, 2, 3. 1, 2. Okay. So these are going 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I counted this one as like 1, 2, 3. This is the origin, -1, -2. 2, 4, 6, 8, 10, 12, 14. We don't have to go that far now. -2, 4, 6, 8, 10, 12. Okay. So then it looks like -1, 19. And let's do it like this, paper. -1, 19 is here. This is -1, 19. We said that's a max, so it's going to behave kind of like this. 2, -10 is here. This is 2, -10. I claim that this was a relative min, so it should behave like this. We got a y-intercept of 12. Let me do these in this color. This color. Y-intercept was 12, which is here, right? So we see that the x-intercept, we can anticipate something like around 1. We could probably go back and do the rational zero test to find that exact. But I'm just going to go with this for now, right? We got a relative max, we got a relative min. Let's go with it. So then if we were to connect it with a smooth curve, again, this is a rough approximation. Now we can go back and do some more analysis to find these x-intercepts, right? But generally something like this, okay? All right, that was a little bit of an adventure, okay? Let's just try another one. And let's go like this. Okay, so what the book did, so now we're generally not going to do it this way, but let's see. So they found a few additional points. They didn't find those intercepts. I was like, yeah, we're not going to have, we weren't expected to find x-intercepts. But like, okay, so they chose several values of x over here on the left, right? -3, blah, 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 blah. -1, 19 was the max. And the man, did we, oh, we got our man wrong. It wasn't negative 19. I think we got negative 10. It was supposed to be negative 8. So I think we just calculated wrong. Negative, when x is 2, let me look at it one more time. When x is 2, 8 times 2 is 16. 16 minus 12 is 4. I think I said 2, right? So that's a 4. So then that's going to be what, negative 20? And then 8. Yeah, I definitely made a mistake there. That should be an 8. Negative 8. But I was just moving fast and trying to do it in my head, but it's okay. And negative 8 there as well. And then so we'd have to adjust our graph, but you know, you get the gist of it. Okay. So what they did, they chose like several values of x, found the corresponding y, and then you see the critical values, right? That's the top of a mountain, the bottom of a valley. That's where the slope, the derivative was 0. So the slope of the tangent line was 0, right? So, you know, we can use the derivative to find those critical values, like this guy and that guy. Let me see my time. So since we're only doing one section per class, I know my past videos we were doing like 35 minutes per section, so I'm going to push this one to 70 minutes, right? Hour and 10 minutes, right? Okay. So we can see some features of the graph from the sketch. Now we'll calculate the coordinates of these features precisely. Find a general expression of the derivative. We did this, right? Determine whether f prime does not exist or where f prime is equal to 0. Since f prime is a polynomial, there is no value where f prime does not exist, so the only possible for the critical value is where the derivative is 0. Okay? We got this. We got all of this, right? So these two critical values partition a number line into 3 intervals. You got section A, B, and C. All right, I think we did this as well. So in section A, I think we chose the same test value. The result was positive. So that means the original function was increasing on that interval. Okay, so when we plug the negative 2 into f prime, when we chose 0 as well, right? If we plug 0 in, we got a negative result. If we plug 0 into f prime, we got a negative result, and so the function was decreasing between those two critical values. And then to the right of 2, I think we chose 3, they chose 4, but in either case, we get that f prime is positive, so the original function is increasing. So by the first derivative test, when x is negative 1, so negative 119 was the relative max, we got that one. And then 2, negative 8 was the relative min. Okay. Notice on, like, for the critical value when x is negative 1, the function goes from increasing to decreasing, so that's why it was a max. And then if we focus on critical value when x is 2, it goes from decreasing to increasing, that's why it was a relative min. Okay. I'm gonna let that be. This is just a practice example. I'm going to leave this as an exercise for you. Find a relative extrema given this, and then sketch the graph. Right? Okay. So with relative extrema, we're just looking at the first derivative. Right? So if we look at f prime of x, that's going to be, so the exponent comes down this 2/3 times this x minus 2 to the power of a negative 1/3, and then I think that's it. Because if we multiply times the derivative of the inside function, it's just going to be times 1, right? So then what we need to do is set this equal to 0. The critical values are going to occur when this is either 0 or undefined. Let's rewrite it. So because we have that negative exponent, that negative 1/3, that's the same as 1 over the cube root. So the thing there is that we cannot divide by 0, right? So if that x minus 2, if we set that equal to 0 and solve, then we have to throw that out, right? Here, let me rewrite it like this. So this is the same as 3 times the cube root of x minus 2 under 2, right? So for a rational function, when will this be zero? This is only going to be zero when the top is zero, right? So the top will never be zero. So then this is going to be undefined if x equals 2, right? So in other words, our critical value, I'm just going to label it as CV, is going to be x equals 2. Because 2 is going to make it undefined, so that's going to be our critical value that we're going to consider. And I think that's the only one, right? So if we were to plot x equals 2 on a number line, I guess that's it. So let's test on the left and the right side of this. So f prime, I'm going to maybe label over here, f prime of x. So this one is 0. On the left side of 2, for instance, if we plug in x equals 0, that's going to be negative 2. Cube root of negative 2 is going to be negative. This whole thing is going to be negative, right? So on the left side, f prime is negative, so that means our function should be decreasing on the left. And then on the right side of 2, maybe something like 3. If we plug in 3, this is going to be 1. Cube root of 1 is still 1, which is positive. The whole thing is going to be positive. So on the right side, the derivative is positive, so the original function should be increasing on the right. Okay. So for the y-intercept, if we set x to 0, that's going to be what? Negative 2 squared is 4, cube root of 4. So the cube root of 4 plus 1, you would have to use your calculator to crunch that number. Yeah, you'd have to use your calculator to crunch that. Okay. So I think we got this. All right, we got this guy here. So we find where f prime does not exist, or where 0. F prime does not exist where the denominator is 0. Oh, dang, this thing like will burn through a battery. I guess we've only been online for like 30 minutes. Okay, there we go. Let's see. So again, the derivative does not exist when the denominator equals 0. Again, the denominator is going to be 0 when x is 2. So then x equals 2 is our critical value. I notice that for this, the denominator equals 0 when the numerator is 0. Since this cannot be equal to 0, there is no solution for f prime is 0. So the only critical value we get is x equals 2, right? So then I think they did the same thing. It should be decreasing on the left, increasing on the right, so we should have a relative min. So 1, let me see. Oh, I forgot to get the actual value. So when x is 2, that's 0, we finish with 1. So then 2 comma 1 is going to be a relative minimum. Okay. Okay. So then if we know this is relative minimum, we just chose several x values on either side, right? So you see the 2 here, then they just chose 1.51. They just chose several x values, found the corresponding y's, and plotted the points. So I'm going to leave this one as an exercise. Let me see my time. I'm so used to these being 35 minutes. Like now it's like I'm primed that I'm ready to like stop the video at 35. But you know what I'll do is at least get through the slides that I have. If I finish the slides, or if we reach like an hour and 10 minutes, whichever comes first, then I'll stop the section. Okay, we're gonna let that be. Okay, I didn't really want to do another quick check. Okay, let's try this one. Find any relative extrema and sketch the graph of the function given by this. Okay. All right. So relative extrema, we look at the first derivative. So that's going to be g prime of x. So we got to use the product rule. So the first times d by dx, or derivative of the second, plus the second times the derivative of the first. Okay. So then that's going to be x squared times the derivative of e is itself times the derivative of the exponent, which is going to be times the negative 1. This comes down. The derivative of x squared is 2x. Okay. Looks like we could factor out x e to the negative x from both terms, right? So we can factor out x e to the negative x from both terms. This leaves us with I'm going to write it like this: 2 minus x, right? Let me look at it one more time. If we distribute, this is going to be 2x e to the negative x, 2x, so that one's taken care of. Negative x times this is going to be negative x squared e to the negative x. Negative x squared e to the negative x, okay? So I feel good about this. So then if we want the critical value, we need to set this equal to 0 and solve, right? So we have the zero factor property. When things multiply to give us 0, basically you set each product to 0, each factor to 0 and solve, right? So critical values, it looks like we get x equals 0. Let's see, e to the negative x, that would be undefined when e is 0, but I don't think we get anything there. So there's nothing for that e to the negative x. And then for 2 minus x, if we solve x equals 2. Let me think about it. So I just got these two critical values. Okay. So then from the original, if x is 0, so then, okay, here. So we need to determine if this is a relative max or min. So say the positive x is in this direction. Say this is our 0, this is our 2. A number to the left of 0, something like negative 1. So we're considering f prime of x, right? To the left of 0, so this is a 0, this is a 0. So to the left of 0, say when x is negative 1, if we plug negative 1 in, this is going to be positive, this is going to be negative. Let's see, negative times positive times positive, so it should be negative. So f prime is negative, so the original function should be decreasing. Okay. A number between 0 and 2 to test is 1. Okay. And so let me see. When x is 1, positive, positive, positive. So f prime is positive, so the original function should be increasing. What do I feel like I might be doing something wrong? Let me think about it. Let's just keep going. To the right of 2, when x is 3, positive, let's see, positive, positive, and negative. So our claim is that it should be decreasing. So then we should have a relative max when x is 0. I think that's the origin. And then, sorry, that's a minimum, because it's going from decreasing to increasing. Hopefully I'm not making too many mistakes. We'll check it and fix it if we are. When x is 2, let me see if we can find that one. e to the negative 2. I'm just going to leave it as 4e to the negative 2. Okay. So then what I would do is maybe choose like, okay, let x be negative 2, negative 1.5. I would choose several, like if we mimic what we did in the previous example, I would choose several values of x around these guys. Something feels a little off, but I'm gonna let it be. Let's look at it. Okay, so we got a minimum value at the origin, a max when x was 2, and whatever that number is, we have to use a calculator to crunch it. Okay, I think we got that x e to the negative x times 2 minus x. Okay. Okay, let's keep going. So yeah, they get 0 and 2. So then if we plot them on a number line, they get decreasing, increasing, decreasing. See, I think that's what we got, decreasing. Okay, so we're okay. I don't know why I wasn't like, I was second guessing myself. Evaluating this at these values, so they get the origin, and this 4e to the minus 2. Okay, and you see it here. And so then we would just make a table, choose several values like around those critical values, and then just plot the corresponding points, and it'll give us a sense of the graph. Wow, we actually did it right. But mostly what I did, I just mimicked. I'm so sleepy. I just mimicked what they did in the previous example. Like once we did that one example, then I was like, okay, well we can do all those steps. So let's just mimic it. We found the critical values by setting the derivative equal to 0. And then we did the first derivative test to see the sign of the first derivative on the left and the right side of each of those critical values. And it satisfied where it went from decreasing to increasing and vice versa. So we were able to identify these as relative max and min. Okay, I know that's like a mouthful. Okay, well, I guess most of the slides were those quick checks. I think I am energetically spent. I kind of want to do one more. I think I might go back and do one of the quick checks. I think I'm spent. I'm gonna go ahead and like stop there, and let's see if there's anything else. Okay, and so we'll get some practice with this. It seems like a lot, but it's not really. It is a lot of information, but you'll start to see how it's the same thing over and over and over with like minor changes, and you just got to try. Like if you push, you can see it. I know like mine was a little bit choppy, but I think you could do it. And you have support too. Like you have a lot of people that's just like sitting here waiting, looking to help, right? With the tutors and myself and your classmates and the internet, like, you know, people, we're here. Like we want to help you guys, but we can't make you, ask for help or whatever. A closed mouth don't get fed. Anyway, um, okay, so on that note, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Peace.